how time itself was born, and why it only flows in one direction. Right now, somewhere on this planet, a glass is falling off a kitchen counter. It strikes the tile floor and detonates into 1,000 glittering pieces, fragments skidding in every direction, water fanning out across the cold surface. You have witnessed this before. Everyone has. And if someone showed you a video of it, you would know immediately, instinctively, without thinking, which direction was forward and which was reverse. 1,000 shards leaping up from the floor, reassembling into a perfect cylinder, water rushing back inside, the glass vaulting up onto the countertop. That would be absurd. That would be a movie played backward. That is not something the universe allows. But here is the thing that has kept physicists awake at night for more than 150 years. If you zoom in far enough, if you look at any single shard of that glass, any individual molecule of water, any lone atom bouncing off the tile, the laws of physics say that its motion is perfectly reversible. Every collision, every trajectory, every interaction between atoms obeys equations that work exactly the same whether time runs forward or backward. Not a single fundamental law of nature, from Newton's mechanics to Einstein's relativity to the equations of quantum mechanics, contains any instruction that says, this way only. Mathematics does not know the difference between past and future, and yet that glass never reassembles. Your coffee never unmixes. You never grow younger. The universe marches relentlessly, stubbornly, heartbreakingly in one direction and one direction only. So what is going on? Why does time have a direction at all? Where did this direction come from? And perhaps the deepest question of all, was there ever a moment when time itself did not exist? When did the clock of the cosmos start ticking, and what wound it up? Tonight, we are going to trace the entire story. From the furnaces of the Industrial Revolution, where engineers first glimpsed the one-way nature of heat, to the deathbed of a tormented Austrian genius who dared to explain why. From the first fraction of a second after the birth of the universe, when all the laws of physics as we know them broke down, to the unimaginably distant future, when the last stars have burned out and even the black holes have evaporated, and time's arrow may finally, quietly, come to a stop. This is the story of how time itself was born, and why it only flows in one direction. We take time for granted. It is possibly the most familiar feature of our existence, so deeply woven into every moment of conscious experience that we rarely stop to wonder what it actually is. We woke up, the hours pass. We eat, we work, we sleep, and another day is done. We mark the passage of years with candles on birthday cakes and lines around our eyes. Time, to us, is as natural as breathing. But the moment you try to define it precisely, something strange happens. It slips through your fingers like water. The philosopher Augustine of Hippo, writing in the 4th century, put it perfectly when he said, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him, I do not know." And that was more than 1,600 years ago. The question has not gotten any easier. Throughout most of human history, time was considered something absolute, a backdrop against which events unfolded, steady and unchanging, the same everywhere in the universe. This was the view of Isaac Newton, who, in his masterwork, the Principia Mathematica of 1687, described what he called absolute, true, and mathematical time, a time that of itself, and from its own nature, flows equably without regard to anything external. In Newton's universe, there was a cosmic clock ticking away in the background, and every object, every event, every observer agreed on what time it was. There was a universal now stretching from one end of creation to the other. This seemed perfectly sensible. After all, it matched our experience. When you and a friend synchronize your watches and then go about your separate days, your watches still agree when you meet again. Clocks tick at the same rate whether they are on a mountaintop or in a valley. Time seemed to be something fixed, something given, something that simply was. But Newton's picture, elegant and intuitive as it was, turned out to be wrong. It took more than 200 years for someone to realize it. And that someone was a young patent clerk in Bern, Switzerland, who had a habit of imagining what it would be like to ride alongside a beam of light. His name was Albert Einstein, and in 1905, with a series of papers that would shake the foundations of physics, he showed that time was nothing like what Newton had imagined. Time was not absolute. Time was not universal. Time was relative, personal, elastic. It bent and stretched and warped depending on how fast you were moving and how strong the gravity was around you. Two people moving at different speeds would disagree about the length of a second. Two clocks at different heights in a gravitational field would tick at different rates. There was no cosmic now, no universal present moment. Just a vast web of events, each with its own local experience of duration. And in 1915, Einstein went even further. His general theory of relativity revealed that time was not merely affected by gravity. Time was part of gravity. Space and time were fused into a single four-dimensional entity called spacetime. And that entity could be warped, curved, and distorted by the presence of matter and energy. The Earth does not orbit the Sun because of some invisible force pulling on it. The Earth follows a curved path through curved spacetime, spacetime that the Sun's enormous mass has bent. And part of that bending is a bending of time itself. Clocks closer to the Sun tick ever so slightly more slowly than clocks farther away. This was a revelation. Time was not a stage on which the universe performed. Time was part of the performance. Time was physical, and if time was physical, then it had properties that could be studied, measured, and explained. It had a beginning. It might have ended. And somehow, for reasons that remain one of the deepest mysteries in all of science, it has a direction. It is worth pausing here to fully appreciate how radical Einstein's departure from Newton really was, because it fundamentally changes what we mean when we talk about time having a direction. In Newton's universe, time was like a river flowing at a constant rate, carrying everything with it. The river was the same everywhere. It flowed at the same speed for everyone. It was, in Newton's own words, absolute. This picture was not merely a philosophical preference. It was baked into the mathematics of Newtonian physics. Newton's equations of motion assume a single, universal time parameter, a cosmic clock that ticks identically for every particle, every planet, every observer in the universe. And for more than 200 years, this assumption worked beautifully. It predicted the orbits of planets, the trajectories of cannonballs, the rhythms of tides with extraordinary precision. But there were cracks, even in Newton's day. Newton himself was uncomfortable with the concept of absolute time, or at least with his inability to ground it in anything observable. He distinguished between what he called absolute time and relative time, the latter being the imperfect approximation we measure with clocks and calendars. But he could not explain what absolute time was made of, or where it resided, or how we could access it. It was a foundation that he could not examine. Einstein demolished that foundation. He showed that there is no river, there is no cosmic clock. There is only the local experience of duration that each observer carries with them, shaped by their motion and their gravitational environment. Two events that are simultaneous for one observer may not be simultaneous for another. The very concept of "at the same time" has no universal meaning. This was not merely an abstract philosophical shift. It had concrete physical consequences. It meant that the question, "how long does it take for something to happen?" does not have a single answer. It depends on who is asking. It depends on where they are. It depends on how they are moving. In Newton's universe, time was simple. In Einstein's universe, time is subtle, slippery, and deeply entangled with the structure of space itself. And this has profound implications for the arrow of time. In Newton's universe, the arrow of time is a mystery that can be cleanly separated from the nature of time itself. Time flows uniformly, and the question is simply why processes within that uniform flow exhibit a preferred direction. But in Einstein's universe, time itself is part of the dynamical system. Time bends, time stretches. Time can, in principle, loop back on itself. The question of the arrow is no longer separate from the question of what time is. They are entangled. The direction of time and the geometry of time are aspects of the same underlying physics. To understand why time flows in one direction, we need to leave the elegant geometry of Einstein's spacetime behind for a moment and travel back to a much earlier era in physics, back to the grimy, soot-stained workshops of the Industrial Revolution, where a different kind of physicist was wrestling with a different kind of problem. Not the nature of space and time, but the practical, brass tacks, coal and steam question of how to build a better engine. It was the early 1800s, and steam power was transforming the world. Factories hummed. Locomotives roared. Ships crossed oceans under the power of boiling water. But the engines that drove all of this were astonishingly inefficient. The best steam engines of the era converted perhaps 5% of the heat from burning coal into useful mechanical work. 95% was wasted, lost to the environment as useless heat. Engineers and inventors desperately wanted to do better, but they did not have a theoretical framework to understand why their engines were so wasteful or how to improve them. Enter Sadi Carnot, a young French military engineer and the son of a prominent politician. In 1824, at the age of just 28, Carnot published a slim volume called Reflections on the Motive Power of Fire, in which he analyzed the fundamental limits of heat engines. Carnot showed that no engine, no matter how cleverly designed, could convert all of its input heat into work. Some heat always had to flow from a hotter source to a cooler sink. There was a theoretical ceiling to efficiency, and it depended only on the temperatures of the hot and cold reservoirs. This was a profound insight, though Carnot himself did not fully grasp its implications. He died of cholera in 1832 at the age of 36, and most of his papers were burned as a precaution against the spread of disease. But his ideas survived, and they fell into the hands of a meticulous German physicist named Rudolf Clausius. Born in 1822 in the Prussian city of Köslin, Clausius was the sixth of 18 children in a family led by a Lutheran pastor who ran his own school. He studied mathematics and physics at the University of Berlin, and by the 1850s, he was at the forefront of a new science that would come to be called thermodynamics, the study of heat and its relationship to energy and work. In 1850, Clausius published a landmark paper that clarified and extended Carnot's work. He articulated the first law of thermodynamics, the conservation of energy, meaning that energy can change form but cannot be created or destroyed. But more importantly, he began to grapple with what would become the second law. He stated it simply at first. Heat does not spontaneously flow from a colder body to a hotter one. A cup of hot coffee sitting on a table will cool down as heat escapes into the surrounding air. The air will never spontaneously concentrate its warmth back into the coffee. Energy flows downhill, from hot to cold, and never the reverse, not without external work being done to force it. Over the next 15 years, Clausius refined and deepened this idea. He realized that every natural process, every transfer of heat, every conversion of energy from one form to another came with a cost. Some fraction of the useful, organized energy was always degraded into a more disordered, less useful form. Energy was conserved in total, yes, but the quality of that energy was forever diminishing. The universe was running down. In 1865, Clausius gave this degradation a name. He chose a word derived from the Greek for transformation. He called it entropy. In a paper presented to the Philosophical Society of Zurich on April 24th of that year, Clausius concluded with two grand statements that summarized the first and second laws of thermodynamics in the most sweeping terms imaginable. The energy of the universe is constant. The entropy of the universe tends to a maximum. It was a bold, almost poetic proclamation. The energy of the cosmos never changes, but the entropy, the measure of disorder and degradation, grows and grows and grows, forever approaching some final maximum state from which there is no return. This was a terrifying idea. If entropy always increases, then the universe is on a one-way journey toward a state of maximum disorder, a state of perfect uniformity where all temperatures are equal. All energy differences have been smoothed out, and nothing interesting can ever happen again. The German physicist Hermann von Helmholtz had already speculated about this possibility, and it came to be known by a haunting name: the heat death of the universe. But Clausius's entropy, powerful as it was, remained somewhat abstract. It was defined in terms of heat and temperature measurable quantities that made sense in the context of engines and furnaces. What it lacked was an explanation. Why did entropy increase? What was happening at a deeper level? What was the microscopic mechanism behind this relentless one-way march? For that, the world would need a very different kind of thinker. The world that Carnot was born into was undergoing one of the most dramatic transformations in human history. The steam engine had been evolving for decades. Thomas Newcomen had built the first practical atmospheric engine in 1712, a clumsy, wheezing contraption used to pump water out of coal mines. James Watt improved upon it in the 1760s and 70s, adding a separate condenser that dramatically increased efficiency, and introducing rotary motion that could drive factory machinery. By the time Carnot sat down to think about the theory behind these machines, steam power was everywhere. It was driving textile mills in Manchester, powering printing presses in London, hauling coal through the Midlands on iron rails. But nobody understood why the machines worked. Not in a deep, theoretical sense. Engineers built better engines through trial and error, through craftsmanship and intuition, through incremental improvements to boiler design and valve timing. There was no science of heat. There was no unified theory that could tell you, from first principles, how much work a given quantity of fuel could produce. This was the problem that consumed Carnot, and what made his analysis so remarkable was its generality. He did not focus on any particular engine design. Instead, he imagined an idealized engine, a perfect, frictionless machine that operated in a cycle, absorbing heat from a hot source, converting some of it into work, and dumping the rest into a cold sink. He then asked what the absolute maximum efficiency of such a machine could be. His answer was startling. The maximum efficiency depended only on the temperatures of the hot and cold reservoirs. It did not depend on the working fluid, whether steam or air or any other substance. It did not depend on the materials or design of the engine. It was a fundamental, universal limit, as inviolable as any law of nature. And crucially, no real engine could ever reach this limit. Real engines always fall short, because real processes always involve some irreversible loss, some wasteful dissipation of useful energy into useless heat. Without knowing it, Carnot had glimpsed the second law of thermodynamics. He had seen that nature imposes a one-way tax on every conversion of heat into work. You can never break even. You can never get back everything you put in. Some portion of the energy in every process is irrevocably degraded. Carnot did not live long enough to develop these ideas further. His premature death robbed physics of what might have been decades of additional insight, but the seed he planted would bloom in the hands of Clausius and Thomson, and eventually Boltzmann. Ludwig Boltzmann was born on February 20th, 1844, in Vienna, Austria. He was a man of enormous intellect, boundless energy, and an almost childlike enthusiasm for the natural world. His colleagues described him as warm, generous, and brilliant, a gifted teacher whose lectures were packed with students. Lisa Meitner, who would later play a crucial role in the discovery of nuclear fission, called him the best teacher she had ever had. He had a sharp wit, once claiming he was tolerably good at mathematics, except when counting beer glasses. He was known for consulting a professor of zoology on the mechanics of milking a cow. But beneath this warm exterior, Boltzmann was a man at war. Not with any person, but with an idea, or rather, with the resistance to an idea that he believed was fundamentally true. Boltzmann was one of the most passionate advocates for the reality of atoms, at a time when many leading scientists considered atoms to be mere mathematical fictions, useful for calculations, but not real physical objects. His life's work was to show that the large-scale behavior of matter, the kind of behavior described by thermodynamics, could be explained by the chaotic motions and collisions of vast numbers of tiny, invisible particles. He began this work in the 1860s, inspired by the Scottish physicist James Clerk Maxwell, who had shown that the properties of gases could be understood statistically by considering the probable distribution of speeds among their molecules. Boltzmann took Maxwell's ideas and ran with them, deeper and further than anyone had before. By 1872, at the age of just 28, he had published groundbreaking papers laying the foundations of what we now call statistical mechanics, the science of connecting the microscopic world of atoms and molecules to the macroscopic world of temperature, pressure, and entropy. Boltzmann's great insight was this: entropy, that mysterious quantity Clausius had defined, was not fundamentally about heat or engines. It was about probability. It was about counting. Imagine a box of gas. The gas consists of trillions upon trillions of molecules, each one zipping around at some speed, in some direction, bouncing off the walls and off each other in a frantic, ceaseless dance. Now, at any given instant, the gas has some large-scale macroscopic state, a particular temperature, pressure, and volume that you could measure with a thermometer and a pressure gauge. But there are astronomically many different microscopic arrangements of all those individual molecules that would produce the same macroscopic measurements. Maybe molecule number 1 is moving fast to the left, and molecule number 2 is moving slowly upward, or vice versa. From the outside, you cannot tell the difference. Both arrangements look exactly the same at the macroscopic level. Boltzmann defined the entropy of a macroscopic state as being related to the number of distinct microscopic arrangements, the microstates, that correspond to it. The more microstates a macrostate has, the higher its entropy. A neatly ordered arrangement where all the gas molecules are clustered in one corner of the box has very few microstates. There are only so many ways to pack all those molecules into a tiny volume. But a disordered arrangement, where the gas is spread evenly throughout the box, has an incomprehensibly vast number of microstates. There are trillions upon trillions upon trillions of ways to arrange those molecules evenly. And this is the key. If you start with the gas in an unusual, low entropy state, say all the molecules crammed into one corner, and then you let the system evolve naturally, what happens? The molecules bounce around randomly. They do not know they are supposed to stay in the corner. They have no preference for order or disorder. They are simply following the basic laws of physics, which are perfectly time-symmetric, but by sheer probability, by the overwhelming statistics of large numbers, the gas will spread out. It will move from its unlikely, low-entropy configuration to a much more probable, high-entropy configuration, not because any law commands it, not because of some mysterious force driving things toward disorder, simply because there are so many more ways to be disordered than to be ordered that the odds of staying in the ordered state are vanishingly, incomprehensibly small. This was Boltzmann's revolution. Entropy increases not because of a fundamental law commanding it, but because it is overwhelmingly, fantastically more probable for entropy to increase than to decrease. The second law of thermodynamics is not a fundamental edict of the universe. It is a statistical truth, a consequence of the mathematics of large numbers. An egg can, in principle, unscramble. The shattered glass can, in principle, reassemble. The laws of physics do not forbid it. But the probability of such an event occurring spontaneously is so absurdly, unimaginably small that you would have to wait far longer than the current age of the universe, many, many times over, for it to happen even once. Boltzmann expressed the relationship between entropy and probability in a formula that would become one of the most famous equations in physics. S equals K times the natural logarithm of Ws is the entropy. W is the number of microstates. And K is a constant, now called the Boltzmann constant, a tiny number that bridges the microscopic world of atoms to the macroscopic world of heat and temperature. That equation was never actually written down by Boltzmann himself in that exact form. It was later rendered explicitly by Max Planck. But it was Boltzmann's idea, his deep insight, his gift to science, and it is engraved on his tombstone in the Zentralfriedhof Cemetery in Vienna, a permanent monument to an idea that changed our understanding of the universe. But Boltzmann's life was shadowed by suffering. Throughout his career, he faced fierce opposition from prominent physicists and philosophers who rejected the atomic hypothesis and dismissed his statistical approach. Ernst Mach, an influential physicist and philosopher in Vienna, was a particularly vocal critic, arguing that atoms were unobservable and therefore unscientific. The intellectual battles took a heavy toll. Boltzmann suffered from severe depression and what some historians believe may have been bipolar disorder. In 1906, while on vacation with his family in Duino, Italy, he took his own life. He was 62 years old. The tragedy of Boltzmann's death is deepened by what came after. Within just a few years of his suicide, the evidence for atoms became overwhelming. In 1905, the same year Einstein published his special relativity paper, he also published a groundbreaking analysis of Brownian motion, the jittery, random dance of tiny particles suspended in a fluid. First observed by the botanist Robert Brown in 1827, Einstein showed that this jittering was caused by the bombardment of invisible molecules, and he derived precise mathematical predictions for how the particles should move. Predictions that could be tested experimentally. The French physicist Jean Perrin took up the challenge. Over a series of meticulous experiments between 1908 and 1911, Perrin measured the Brownian motion of microscopic particles and confirmed Einstein's predictions with extraordinary precision. He was even able to calculate Avogadro's number, the number of atoms in a mole of substance, from his observations. The results were definitive. Atoms were real. They were not mathematical fictions. They were tangible, physical objects whose existence could be demonstrated beyond any reasonable doubt. Perrin was awarded the Nobel Prize in Physics in 1926 for this work. In his acceptance speech, he acknowledged the intellectual debt owed to Boltzmann's statistical mechanics, the very framework that Mach and others had so viciously attacked. If Boltzmann had lived just a few more years, he would have seen his life's work vindicated. He would have witnessed the complete triumph of the atomic hypothesis. He would have known that he was right all along. Instead, he died believing himself a failure. He died thinking that his great contribution to science might be forgotten, or worse, discredited. It is one of the saddest stories in the history of physics, and the equation carved into his gravestone, S equals K log W, stands not just as a monument to a beautiful idea, but as a rebuke to the cruelty of intellectual fashion and the fragility of the human spirit. Boltzmann's insight deserves a closer look, because it is so powerful, so counterintuitive, and so central to everything that follows. Let us take a simple example and really sit with it. Imagine you have a room with a thin partition running down the middle. On the left side, you have placed 100 molecules of gas. On the right side, nothing, pure vacuum. Now you remove the partition. What happens? The molecules begin to spread out. They bounce off the walls, off each other, through the space where the partition used to be, into the empty right half of the room. Within moments, the gas is more or less evenly distributed. This is completely unsurprising. It is exactly what you would expect. But now consider the reverse. Could the gas, starting from a uniform distribution, spontaneously collect itself back into the left half? Could every molecule, by pure chance, happen to be moving leftward at just the right moment? In principle, yes. The laws of physics do not forbid it. Each molecule is following perfectly reversible laws of motion. There is nothing in Newton's equations that prevents all the molecules from ending up on the same side. But the probability is absurdly small. For 100 molecules, the probability of all of them being in the left half at any given instant is roughly 1 in 2 to the 100th power, which is approximately 1 in 10 to the 30th power. That is a 1 followed by 30 zeros. If you checked on the gas once every second, you would have to wait roughly a billion seconds, which is much longer than the current age of the universe, to have a reasonable chance of finding all the molecules on one side, and that is for just 100 molecules. A room full of air contains something like 10 to the 25th molecules. The probability of them all being in one half of the room is so staggeringly, incomprehensibly tiny that it makes the previous number look enormous by comparison. It is a number so close to zero that no analogy can convey its smallness. It is not merely unlikely. It is, for all practical purposes, impossible. This is the statistical heart of the second law. Entropy increases not because the universe commands it, but because the numbers are overwhelmingly in favor of it. There are so many more disordered arrangements than ordered ones that the odds of spontaneously moving from disorder to order are effectively nil. But notice something crucial. The statistical argument only works in one direction if you assume a special starting point. If you pick a random moment in the life of the gas, a moment when it is already uniformly distributed, then the gas is equally likely to become slightly more concentrated or slightly less concentrated. The statistics are symmetric. There is no arrow. The arrow only appears if you know or assume that the gas started in a low entropy state with all the molecules on one side. And this is a great puzzle. Why did the universe start in a low entropy state? The statistical argument explains why entropy increases from any given starting point, but it does not explain the starting point itself. For that, we need cosmology. We need to understand the Big Bang. And this is what links the physics of steam engines and playing cards to the origin of the cosmos. Boltzmann himself sensed this connection. In some of his later writings, he speculated that perhaps the universe is, on the whole, in a state of thermal equilibrium, and our observable portion is merely a rare fluctuation, a temporary dip in entropy that happened by chance. In a sufficiently large universe, such fluctuations are inevitable, however unlikely. And we, as observers, could only exist during such a fluctuation, because life requires the low entropy conditions that make complex chemistry and biology possible. This idea was remarkably prescient. It anticipated, by more than a century, many of the themes that dominate modern cosmology, including the multiverse, the anthropic principle, and the Boltzmann brane problem. The Boltzmann brane problem is particularly troubling. If the universe is fundamentally in equilibrium, and our low entropy environment is just a fluctuation, then the most likely fluctuation that produces an observer is not an entire universe full of galaxies and stars. It is a single brane, popping into existence out of the thermal noise, complete with false memories of a non-existent past, only to dissolve back into chaos an instant later. Such a disembodied brane, called a Boltzmann brane, is astronomically more likely than an entire ordered universe, simply because it requires a much smaller fluctuation. This is a deeply unsettling idea, and most physicists take it as evidence that the Boltzmann fluctuation model is wrong. Our universe is not a random fluctuation in a state of equilibrium. Something deeper is going on. The initial conditions of the universe are not accidental. They are a fundamental feature of cosmology that needs to be explained. In 1867, just 2 years after Clausius named entropy, the Scottish physicist James Clerk Maxwell proposed a thought experiment that would haunt thermodynamics for over a century. He imagined a tiny, intelligent being, later dubbed Maxwell's Demon by William Thomson, stationed at a small trapdoor between 2 chambers of gas at equal temperatures. The demon watches individual molecules approaching the door. When a fast-moving molecule comes from the left, the demon opens the door and lets it pass to the right. When a slow-moving molecule comes from the right, the demon opens the door and lets it pass to the left. Over time, the right chamber fills with fast, hot molecules, and the left chamber fills with slow, cold molecules. A temperature difference has been created from nothing. Heat has flowed from cold to hot. The second law has been violated. Or has it? Maxwell's demon caused enormous controversy and generated decades of debate. The resolution, which emerged gradually through the work of Leo Szilard in 1929, Leon Brillouin in the 1950s, and Charles Bennett and Rolf Landor in the 1960s and 80s, is subtle and beautiful. The key insight is that the demon must process information. To sort molecules, the demon must observe them, record their speeds, and decide whether to open or close the door. All of this requires information processing, and information processing has a thermodynamic cost. Specifically, Landor showed in 1961 that erasing 1 bit of information, resetting a memory register from an unknown state to a known state, necessarily releases a minimum amount of heat into the environment. This minimum, called Landor's limit, is roughly 3 times 10 to the negative 21 joules per bit at room temperature. It is tiny, but it is non-zero. And Bennett showed in 1982 that the demon must eventually erase its accumulated records, or its memory will overflow. And the heat released by this erasure is exactly enough to compensate for the entropy decrease achieved by the sorting. The second law survives, but its survival hinges on a remarkable connection between information and thermodynamics. Entropy is not just about disorder in the physical sense. It is about information, about what we know and what we do not know about the microscopic state of a system. High entropy means many possible microstates, which means less information about which specific microstate the system is in. Low entropy means fewer possible microstates, which means more information. This connection between entropy and information was formalized by the mathematician Claude Shannon in 1948 in a foundational paper that launched the field of information theory. Shannon showed that the mathematical formula for information entropy is identical in form to Boltzmann's formula for thermodynamic entropy. This was initially seen as a coincidence or a mathematical analogy, but physicists have increasingly come to believe that the connection is deep and fundamental. Information is physical. Bits are real. And the destruction of information, the erasure of knowledge, generates heat and increases the entropy of the universe. This is yet another thread connecting the arrow of time to the deepest structures of physics. The arrow of time is not just about heat and disorder. It is about knowledge and ignorance, about the fact that the universe relentlessly erases information, smoothing it out, spreading it thin, carrying it toward a state where everything is known in the average and nothing is known in the particular. There is one more historical episode worth mentioning. because it struck at the very heart of Boltzmann's program and forced him to confront the deepest question about the arrow of time. In 1876, Boltzmann's colleague Joseph Loschmidt raised a devastating objection. If the microscopic laws of physics are time-reversible, Loschmidt argued, then for every sequence of molecular motions that leads to an increase in entropy, there is an equally valid sequence, just with all the velocities reversed, that leads to a decrease in entropy. You cannot derive a time-asymmetric result, like the second law, from time-symmetric premises, like Newton's laws. The argument was simple, elegant, and apparently fatal to Boltzmann's statistical approach. Boltzmann took the objection seriously. His response, which would take years to fully develop, was essentially this. Loschmidt was right that both directions are permitted by the laws of motion, but the number of microstates leading to entropy increase is overwhelmingly larger than the number leading to entropy decrease. If you start in a low entropy state, almost every possible future evolution leads to higher entropy, and almost every possible past evolution also leads to higher entropy. The low entropy state sits at the bottom of an entropy valley, with entropy increasing in both temporal directions. This seems paradoxical. If entropy increases toward the future and also increases toward the past, then the entropy was higher in the past too, which contradicts observation. Boltzmann resolved this by pointing out that we must condition on what we know. We know the current state of the universe. We know it was in a lower entropy state in the past because we have records and memories that tell us so. These records themselves are low entropy structures that exist only because the universe started in a low entropy state. Without the low entropy initial condition, there would be no records, no memories, and no arrow of time. Loschmidt's objection did not destroy Boltzmann's program. Instead, it sharpened it. It forced Boltzmann, and every physicist who came after him, to confront the fact that the arrow of time cannot be derived from the laws of physics alone. It requires an additional ingredient: the special initial conditions of the universe. The laws tell you the rules. The initial conditions tell you the starting position. And it is the starting position, not the rules, that gives time its direction. With Boltzmann's statistical framework in hand, the pieces were in place for someone to put a name on the deep mystery at the heart of it all. That someone was Arthur Stanley Eddington, the British astrophysicist who would become one of the most celebrated scientists of the early 20th century. Eddington is perhaps best known for organizing the 1919 solar eclipse expedition that confirmed Einstein's prediction that gravity bends light, a result that launched Einstein into worldwide fame. But Eddington was much more than a skilled observer. He was a profound thinker about the nature of the universe, and in 1927, in his Gifford Lectures at the University of Edinburgh, later published as a book called The Nature of the Physical World in 1928, he gave the phenomenon a name that has stuck ever since. He called it the arrow of time. Eddington wrote with a clarity and elegance that few physicists have matched. He said, "Let us draw an arrow arbitrarily. If as we follow the arrow, we find more and more of the random element in the state of the world, then the arrow is pointing towards the future. If the random element decreases, the arrow points towards the past. That is the only distinction known to physics." And then he added, "I shall use the phrase time's arrow to express this one-way property of time which has no analog in space." This was a remarkable statement. In space, you can move left or right, up or down, forward or backward with equal ease. There is no preferred direction. But in time, there is. And the only way physics knows to identify that preferred direction is through the increase of entropy, the growth of randomness and disorder. The arrow of time, Eddington was saying, is the arrow of entropy. Eddington also held entropy in extraordinarily high regard among the laws of physics. He famously declared that if someone pointed out that your pet theory of the universe disagreed with Maxwell's equations, then so much the worse for Maxwell's equations. If it was contradicted by observation, well, experimentalists sometimes bungle things. But if your theory was found to violate the second law of thermodynamics, he said, he could give you no hope. There was nothing for it but to collapse in deep humiliation. For Eddington, the second law was the supreme law. In the decades that followed, physicists refined the concept of the arrow of time and realized that there was not just one arrow, but potentially several, which appeared to be aligned with one another. Stephen Hawking, in his work on cosmology and black holes, identified at least 3 distinct arrows. The first is the thermodynamic arrow, the one Eddington described, the direction in which entropy increases. This is the arrow that makes eggs break, but not unbreak. That makes ice melt in warm water, but never spontaneously refreeze. It is the arrow embedded in every irreversible process we observe. The second is the psychological arrow, the direction in which we perceive time to pass. We remember yesterday, but not tomorrow. We can influence the future, but not the past. Our brains record memories in the direction of increasing entropy, because the process of forming a memory is itself an entropy-increasing process. To remember something is to create a correlation between your brain and the outside world, and creating correlations increases the total entropy of the combined system. This is why, as Sean Carroll has pointed out, without entropy increasing, there would be no memory of the past. Without entropy increasing, there would be no causal effect that we could have on the future. Without the growth of disorder, nothing interesting would happen at all. The third is the cosmological arrow, the direction in which the universe is expanding. Since the Big Bang, the universe has been getting larger, with galaxies moving apart from one another and space itself stretching. This expansion is linked, in complex ways, to the thermodynamic arrow. Because the expanding universe allows entropy to continue increasing by continually creating more room, more available states, more possible configurations. All 3 of these arrows point in the same direction. And that is deeply puzzling, because there is no obvious reason why they should. Each arrow arises from a different area of physics: thermodynamics, neuroscience, cosmology. The fact that they all agree, that they all point from past to future, suggests that they are all rooted in the same underlying cause. And that cause, most physicists believe, lies in the conditions at the very beginning of the universe. But before we go there, before we journey back to the first fraction of a second after creation, there is one more puzzle we need to confront. One more layer to the mystery. Because the arrow of time is not just puzzling, it is paradoxical. To appreciate how strange the arrow of time is, let us dwell for a moment on the nature of physical law. Imagine you are watching a perfectly filmed movie of 2 billiard balls colliding on a frictionless table. The cue ball strikes the 8 ball. The 8 ball rolls away. The cue ball slows down. Now imagine the film played backward. The 8 ball rolls toward the cue ball. They collide. The cue ball rolls away. Everything looks perfectly natural. You could not tell, from the physics alone which version was the forward one and which was the reverse. Now imagine watching a movie of an ice cube melting in a glass of warm water. The ice cube shrinks. The water cools slightly. A puddle of meltwater appears. If you play this backward, you see the puddle spontaneously freeze, an ice cube forming out of the water, the glass getting warmer. This looks ridiculous. It looks obviously wrong. You can instantly tell that the film is being played backward. But here is the astonishing thing. At the level of individual molecules, the melting ice cube is made up of nothing but billiard ball-like collisions. Water molecules in the warm liquid slam into the molecules of the ice crystal, knocking them loose. Each individual collision is perfectly reversible. Each individual molecular interaction obeys Newton's laws just as faithfully backward as forward. The irreversibility of the melting ice cube is not encoded in any single collision. It emerges only from the statistics of vast numbers of collisions, all starting from a particular ordered initial arrangement. This is what physicists mean when they say that irreversibility is not fundamental. It is emergent. It arises from the coarse-grained, macroscopic description of a system. At the microscopic level, every process is reversible. At the macroscopic level, some processes appear irreversible. The difference is not in the laws. It is in the starting conditions and in our inability to track every individual molecule. Think about what this means for your everyday experience. Right now, your body is a fantastically complex arrangement of trillions of cells, each one containing billions of molecules, all organized in an intricate hierarchy of structures, from organelles to cells to tissues to organs. This organization represents an extremely low entropy state. There are vastly more ways to arrange those atoms into a disorganized heap than into a living, functioning human being. And so, left to its own devices, your body would simply fall apart. It would decay, decompose, and return to a disordered state. This is not morbid speculation. This is the second law of thermodynamics in action. The only reason you remain alive, the only reason your entropy stays low from moment to moment, is that you are constantly importing low entropy energy from the environment in the form of food and exporting high entropy waste heat. You are an open system, riding the great river of increasing entropy, maintaining your local island of order only by contributing to the disorder of the wider universe. And the energy you consume traces ultimately back to the sun, which pours low-entropy photons of visible light onto the Earth and receives, in return, a much larger number of high-entropy infrared photons radiated back into space. The sun, in turn, derives its energy from the gravitational collapse of hydrogen gas, a process that increases the overall entropy of the universe. And the gravitational potential energy that makes this collapse possible is a consequence of the smooth, low-entropy initial conditions of the Big Bang. Everything connects. The arrow of time in your kitchen, the arrow of time in your body, the arrow of time in the sun, and the arrow of time in the cosmos are all the same arrow. They all trace back to the same source, the extraordinarily low entropy beginning of the universe. Here is the paradox, stated as simply as possible. Every fundamental law of physics we have ever discovered is symmetric in time. Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's equations of general relativity, the Schrödinger equation of quantum mechanics. Every single one of these theories works perfectly well whether you run the clock forward or backward. If you filmed the orbit of a planet around a star and played the film in reverse, the backward orbit would obey Newton's laws just as faithfully as the forward one. If you filmed a beam of light reflecting off a mirror, the reversed film would satisfy Maxwell's equations just as precisely. At the most fundamental level, the universe does not know which way time is supposed to go. This is called time-reversal symmetry, or T-symmetry, and it is one of the deepest properties of the laws of physics. A ball thrown into the air follows a parabolic arc. Film it and play it backward, and you see a ball following a perfectly valid parabolic arc, just in the opposite direction. The laws do not care. They work either way. Now, at first glance, this seems to be in flat contradiction with everything we just discussed. If the laws of physics are time-symmetric, why does time have a direction? Why does entropy increase? Why do glasses shatter but never reassemble? The answer, as Boltzmann showed, is that the arrow of time does not come from the laws. It comes from the initial conditions. The laws of physics are like the rules of a board game. They tell you what moves are allowed, but they do not tell you where to place the pieces at the start. The starting arrangement is a separate input. And if you start with a very special, very unusual, very low entropy arrangement, then the laws of probability will virtually guarantee that the system evolves toward higher entropy. Not because the laws command it, but because the starting point was so unlikely that almost any change will move the system toward something more probable. Imagine shuffling a brand new deck of cards. The deck starts in perfect order, aces through kings, sorted by suit. That is a very special, very low probability arrangement. Now shuffle it. The laws of card shuffling are perfectly reversible. Any sequence of shuffles that takes you from order to disorder could, in principle, be reversed to take you back. But you will never, in practice, shuffle a randomized deck back into perfect order. The odds are roughly 1 in 10 to the 68th. You would have to shuffle continuously for longer than the age of the universe to have a reasonable chance of it happening. And a deck of cards has only 52 elements. The universe has something like 10 to the 80th particles. But this answer, satisfying as it is, only pushes the mystery back one step. If the arrow of time comes from the initial conditions, then we need to explain those conditions. We need to explain why the universe began in a state of such extraordinarily low entropy. And that takes us to the beginning of everything. Before we go there, though, we should note that time-reversal symmetry is not quite as perfect as we have made it sound. There is, in fact, a tiny crack in the symmetry of time at the fundamental level. It was discovered in 1964 by James Cronin and Val Fitch at Brookhaven National Laboratory, and it involved one of nature's most peculiar particles, the neutral kaon. The neutral kaon is an unstable particle made of a quark and an antiquark, and it has a remarkable property. It can oscillate back and forth between its matter and antimatter forms. Cronin and Fitch discovered that the rate at which the kaon transforms into its antiparticle is not exactly the same as the rate at which the antiparticle transforms back. There is a tiny asymmetry, a minuscule bias. This violated a symmetry called CP symmetry, the combined symmetry of charge conjugation, swapping particles for antiparticles, and parity, reflecting the system in a mirror. And since the laws of physics are believed to obey a deeper symmetry called CPT symmetry, the combined symmetry of charge, parity, and time reversal, a violation of CP automatically implies a violation of T. time-reversal symmetry, is not quite perfect. This discovery was confirmed directly by the CPLEAR experiment at CERN in 1998, which measured the rates of kaon to antikaon and antikaon to kaon oscillations, and found that they were indeed different. The arrow of time exists even in the behavior of individual subatomic particles. But here is the crucial point, emphasized repeatedly by physicists like Sean Carroll. This particle physics violation of time-reversal symmetry is not the arrow of time that we experience. The rates of kaon oscillation are almost identical in both directions. The asymmetry is tiny, roughly 7 parts in 1,000. More importantly, neutral kaons play absolutely no role in the everyday processes that define the arrow of time, like eggs scrambling, ice melting, or people aging. Those processes are driven entirely by entropy and statistics, not by the weak nuclear force that governs kaon decay. The particle physics arrow of time is a subtle, delicate effect. The thermodynamic arrow of time is overwhelming, universal, and inescapable. They are not the same thing, and so the central question remains: why does entropy increase? Why did the universe begin in a state of low entropy? What happened at the beginning? To answer these questions, we need to go all the way back. Back before there were stars, before there were atoms, before there was even a meaningful distinction between past and future. Back to the moment when time itself came into existence. The universe is approximately 13.8 billion years old. We know this with remarkable precision, thanks to decades of observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. But when we say that the universe is 13.8 billion years old, what we really mean is that 13.8 billion years ago, the universe was in a state so extreme, so far beyond anything we can recreate in a laboratory or even fully comprehend, that our most fundamental theories of physics simply break down. We call that initial state the Big Bang, but the name is misleading. It was not an explosion in the conventional sense. There was no pre-existing space into which matter was flung. There was no outside. The Big Bang was not an event that happened at a particular location in a pre-existing universe. It was the beginning of the universe itself, the beginning of space, and as far as our best theories can tell us, the beginning of time. To understand what this means, imagine rewinding the history of the cosmos like a film played in reverse. Galaxies rush toward each other. Stars collapse back into clouds of gas. The cosmic microwave background radiation grows hotter and brighter. The universe shrinks. It gets denser, hotter. The atoms break apart into free protons, neutrons, and electrons. The protons and neutrons dissolve into quarks and gluons. The fundamental forces of nature, which in our current universe are 4 distinct interactions: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, begin to merge back together. And then we reach a boundary, a wall in our understanding, a moment so early, so extreme, that our most powerful theories cannot see past it. This boundary is called the Planck epoch, named after the German physicist Max Planck, who in 1899 proposed a system of fundamental units based on the constants of nature. The Planck time is approximately 10 to the negative 43rd seconds. That is a decimal point followed by 42 zeros, and then a 1. It is an interval so short that it makes a nanosecond look like an eternity. The Planck length, the distance light can travel in one Planck time, is about 10 to the negative 35th meters, a distance so small that an atom looks like a galaxy by comparison. And the Planck temperature, the temperature of the universe during this epoch, was around 10 to the 32nd degrees Kelvin, a heat so intense that it defies any meaningful comparison to anything in our experience. During the Planck epoch, the universe was so small, so dense, and so hot that gravity itself behaved as a quantum force. In our everyday experience, and indeed in all of physics as we currently understand it, gravity and quantum mechanics occupy separate domains. Gravity governs the very large, the orbits of planets, the bending of light around stars, the expansion of the cosmos. Quantum mechanics governs the very small, the behavior of electrons, the emission of photons, the decay of radioactive nuclei. In normal circumstances, their jurisdictions do not overlap. But during the Planck epoch, the entire observable universe was compressed into a region smaller than an atom. And at that scale, gravity and quantum mechanics cannot be separated. You need a theory that combines them. You need a theory of quantum gravity, and we do not have one. This is one of the great unsolved problems in physics. We have candidates. String theory proposes that the fundamental constituents of nature are not point-like particles, but tiny, vibrating loops of energy. And it naturally incorporates gravity in a quantum framework. Loop quantum gravity takes a different approach, suggesting that spacetime itself is quantized, made up of discrete units at the Planck scale, woven together like a fabric of interlocking loops. Both approaches have yielded important insights, but neither has yet produced a complete, experimentally verified theory. Without a theory of quantum gravity, we cannot describe what happened during the Planck epoch. We cannot say whether time existed in any meaningful sense during that first 10 to the negative 43rd seconds. We cannot say what, if anything, came before the Big Bang. Indeed, the question itself may be meaningless. If time was born in the Big Bang, then asking what came before is like asking what is north of the North Pole. The question presupposes a framework that does not apply. This was an analogy that Stephen Hawking was particularly fond of, and it lies at the heart of one of the most audacious proposals in the history of cosmology. In 1983, Hawking, working with the American physicist James Hartle, proposed what they called the no-boundary proposal. The idea is breathtaking in its simplicity and its strangeness. Hawking and Hartle suggested that as you trace the history of the universe backward toward the Big Bang, time does not abruptly end at a singularity. Instead, time gradually transforms into something else. It becomes what physicists call imaginary time, a mathematical construction in which the time dimension behaves more like a dimension of space. In this picture, space-time near the Big Bang is smooth and rounded, like the surface of a sphere. Just as the surface of the Earth has no edge, no boundary, no point where you fall off, the space-time of the early universe has no boundary in time. There is no first moment. Time does not begin. It simply fades into existence, emerging from a timeless geometry like a river emerging from a spring. In Hawking's own words, delivered in a lecture he gave on the subject, our model became known as the no-boundary proposal. It says that when we go back towards the beginning of our universe, space and time become fuzzy and cap off, somewhat like the South Pole on the surface of the Earth. Asking what came before the Big Bang is meaningless, according to the no-boundary proposal, because there is no notion of time available to refer to. It would be like asking what lies south of the South Pole. The no-boundary proposal is elegant, but it remains controversial. Some physicists have raised serious mathematical concerns about whether the proposal actually produces a universe that looks like ours. Others have proposed alternative models, like the tunneling proposal of Alexander Vilenkin, in which the universe quantum tunnels into existence from literally nothing. And still others have explored cyclic models, in which our Big Bang is not the beginning of everything, but merely the latest in an eternal series of cosmic expansions and contractions. What all of these proposals share is a recognition that the birth of the universe is intimately connected to the birth of time. Time, in these models, is not a pre-existing stage on which the cosmic drama unfolds. Time is part of the drama. It is created, or it emerges, or it transforms as part of the process that brings the universe into being. And this has profound implications for the arrow of time, because it means that the low entropy initial conditions that give rise to the thermodynamic arrow are not imposed from the outside. They are part of the fabric of creation itself. Let us slow down here and try to really absorb what the Planck epoch means, because it is one of the most extraordinary concepts in all of science. You are trying to imagine a condition in which the entire observable universe, everything you can see in every direction, all the stars, all the galaxies, all the billions of light years of space, is compressed into a region smaller than a proton. Not just the matter, the space itself. And at this scale, the geometry of spacetime is not the smooth, continuous fabric that Einstein described. It is a roiling, churning chaos that the physicist John Wheeler called quantum foam. In this quantum foam, the very concepts of here and there, before and after, lose their meaning. Space and time are not fixed. They are fluctuating wildly, forming tiny wormholes and black holes that appear and disappear in intervals shorter than the Planck time. Causality, the idea that causes precede their effects, breaks down. The smooth, flowing river of time that we experience is nowhere to be found. There is only a frothy, turbulent sea of quantum geometry, in which the distinction between past and future has not yet crystallized. Some physicists have tried to describe this state using the language of loop quantum gravity. In loop quantum gravity, spacetime at the Planck scale is not continuous. It is discrete, made up of tiny, quantized units. Space is like a fabric woven from loops of gravitational field, forming a network called a spin network. Time, in this picture, is the process by which one spin network transitions to another. At the Planck scale, these transitions are not ordered in a single, flowing sequence. They are spread out, superimposed, uncertain. Time, as we understand it, has not yet emerged. Others have tried to describe it using string theory, in which the fundamental objects are not point particles, but tiny, one-dimensional strings vibrating at different frequencies. In string theory, the Planck scale is the realm where the strings themselves become important, where the extra dimensions of space predicted by the theory are curled up into tiny shapes too small to observe, and where the familiar four-dimensional spacetime emerges only as an approximation valid at much larger scales. But regardless of the theoretical framework, the message is the same. At the Planck scale, at the very beginning, time as we know it does not exist. It emerges, it crystallizes, it comes into being through some process that we do not yet fully understand. And with its emergence comes the arrow, the low entropy initial state, the seed from which all of cosmic history will grow. After the Planck epoch, things happened fast, fantastically, unimaginably fast. At around 10 to the negative 36th seconds after the beginning, something extraordinary is believed to have occurred. The universe underwent a period of cosmic inflation, a brief but violent expansion in which the fabric of space stretched by a factor of at least 10 to the 26th, possibly much more, in a time interval shorter than the blink of an eye. A region smaller than an atom was inflated to a size larger than the entire observable universe today. Inflation was proposed in 1981 by the physicist Alan Guth as a way to solve several puzzles in the standard Big Bang model. Why is the universe so uniform on large scales? Why is it so geometrically flat? Inflation answers these questions by stretching any initial irregularities into smoothness, much like inflating a crinkled balloon until its surface appears flat. And the tiny quantum fluctuations present during inflation were also stretched to cosmic scales, seeding the slight density variations that would eventually grow under the pull of gravity into the galaxies and galaxy clusters we observe today. These density variations are visible in the cosmic microwave background, the faint afterglow of the Big Bang that was first detected in 1964 by Arno Penzias and Robert Wilson at Bell Labs in New Jersey. Penzias and Wilson were not looking for the cosmic microwave background. They were testing a sensitive microwave antenna and found a persistent hiss of static that they could not eliminate. They checked the equipment, cleaned pigeon droppings from the antenna, rebuilt parts of the detector, and still the noise remained. Eventually, they learned that a group of physicists at Princeton, led by Robert Dicke, had been preparing to search for exactly this kind of signal, the remnant heat of the Big Bang, predicted decades earlier by the physicist George Gamow and his collaborators Ralph Alpher and Robert Herman. Penzias and Wilson had stumbled upon one of the most important discoveries in the history of cosmology. They were awarded the Nobel Prize in Physics in 1978. The cosmic microwave background is a snapshot of the universe, as it was roughly 380,000 years after the Big Bang, the moment when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. It shows a universe that is astonishingly uniform, with temperature variations of only about 1 part in 100,000. This near-perfect uniformity is a direct consequence of the low entropy initial conditions, smoothed further by inflation. And those tiny 10 parts per million variations are the seeds of all the structure we see today. Every galaxy, every star, every planet, every living thing. After the cosmic microwave background was released, roughly 380,000 years after the Big Bang, the universe entered what cosmologists call the cosmic dark ages. This was a period lasting several hundred million years, during which no stars had yet formed. The universe was filled with neutral hydrogen and helium gas, slowly cooling, slowly expanding, lit by nothing but the fading glow of the cosmic microwave background. It was dark, profoundly, absolutely dark. No point of light anywhere, just an immense, expanding cloud of gas in a blackness more complete than anything we can imagine. The temperature of the background radiation dropped steadily, passing through the range where it would have been visible as a faint red glow, then into the infrared, then into the microwave. The universe was cooling toward absolute zero, but the darkness contained seeds. Those tiny fluctuations imprinted by inflation, the slight variations in density that appeared as hot and cold spots in the cosmic microwave background, were doing their silent work. In regions where the density was slightly higher than average, gravity was slightly stronger. Gas was being pulled inward, accumulating, compressing. Over millions of years, these subtle density enhancements grew, amplified by gravity's patient, relentless pull. And then, somewhere between 100 and 200 million years after the Big Bang, something extraordinary happened. In the densest regions, the gas had been compressed and heated enough that hydrogen nuclei began to fuse together, releasing energy. The first stars ignited. These first stars were nothing like our sun. They were monsters. With no heavy elements to cool the collapsing gas clouds, the first stars are believed to have been hundreds of times more massive than the sun, blazing with millions of times its luminosity, their surfaces burning at temperatures that dwarfed anything in the modern universe. They were brilliant, brief, and violent, burning through their hydrogen fuel in just a few million years before exploding as supernovae, scattering heavy elements, carbon, oxygen, silicon, iron, into the surrounding gas for the first time. These heavy elements, forged in the nuclear furnaces of the first stars and scattered by their deaths, would go on to form the next generation of stars, and the next, and eventually the rocky planets, the organic molecules, and the living organisms that would one day look up at the sky and wonder where they came from. Every atom of carbon in your body, every atom of iron in your blood, every atom of calcium in your bones was forged inside a star that died before the sun was born. You are, quite literally, made of stardust, and every one of those stellar furnaces, every one of those supernova explosions, was a step along the great entropy staircase, a further increase in the disorder of the universe, powered by the low entropy initial conditions of the Big Bang. The formation of galaxies followed. Gravity pulled the first stars and gas clouds together into larger and larger structures, filaments and sheets of matter stretching across millions of light years, with vast, nearly empty voids between them. This large-scale structure of the cosmos, the cosmic web, is itself a consequence of those primordial density fluctuations, amplified by billions of years of gravitational evolution. And at the centers of many galaxies, matter fell inward to form supermassive black holes, objects containing millions or billions of times the mass of the sun, engines of entropy whose gravitational influence would shape the evolution of their host galaxies for billions of years. Our own galaxy, the Milky Way, assembled over billions of years from the merger of smaller galaxies and the steady accumulation of gas from intergalactic space. Our sun formed about 4.6 billion years ago from a cloud of gas enriched by the debris of earlier stellar generations. The Earth formed shortly after, and within a few 100 million years, life appeared on its surface, feeding on the low entropy energy of sunlight, increasing the entropy of its environment, riding the arrow of time toward ever greater complexity. All of this, from the first star to the last thought in your mind, is a consequence of the second law of thermodynamics in action. It is increasing entropy. It is the universe sliding down the long, gentle slope from its improbable beginning toward its inevitable end. And this brings us to what many physicists consider the deepest puzzle in all of time physics, the puzzle that lies at the root of everything. Why did the universe begin in a state of such extraordinarily low entropy? This question has a name: The philosopher David Albert called it the past hypothesis, and the physicist Sean Carroll of Johns Hopkins University has spent much of his career thinking about it. The past hypothesis is simply the observation that the early universe was in a state of remarkably low entropy. Not zero entropy, but enormously lower than it could have been. And this low entropy beginning is, in some sense, the entire explanation for the arrow of time. Think about it this way. If the universe had begun in a state of maximum entropy, in a state of complete thermal equilibrium with no temperature differences, no density variations, no structure whatsoever, then entropy could not have increased because it was already at its maximum. There would be no thermodynamic arrow. There would be no distinction between past and future. Nothing interesting would ever happen. The universe would be a featureless, unchanging fog forever. But that is not how the universe began. The universe began in a hot, dense, remarkably smooth state. A state in which energy was distributed almost, but not quite, uniformly. This near uniformity might seem like it should correspond to high entropy. After all, a gas spread evenly through a box is in a high entropy state. But here is where gravity changes everything. In a universe where gravity is important, and our universe is very much such a universe, a smooth, uniform distribution of matter is actually a very low entropy state. Gravity wants to clump things together. It wants to pull matter into dense concentrations, into stars, into galaxies, ultimately into black holes. A universe full of black holes is a much higher entropy state than a universe of smooth, evenly distributed gas. So the smooth, hot, uniform early universe was, from gravity's perspective, exquisitely ordered. It was a state of fantastically low gravitational entropy. And that low entropy beginning is the reason for everything. It is the reason stars can shine. Because the gravitational collapse that forms stars increases entropy. It is the reason life can exist. Because living organisms feed on the low entropy energy of starlight and excrete high entropy, waste heat. It is the reason you can remember the past and plan for the future. It is the reason eggs can break, coffee can cool, and time can flow. As Carroll puts it, everything that happens in the universe to distinguish the past from the future is ultimately because the entropy is lower in one direction and higher in the other. The entire rich, complex, beautiful, heartbreaking story of the cosmos, from the formation of the first galaxies to the evolution of life on Earth to you, right now, listening to these words, is a consequence of the universe starting in a state of low entropy and gradually, inexorably, evolving toward higher entropy. The arrow of time is the universe sliding downhill on the slope of entropy, away from that improbable beginning. But why? Why did the universe start this way? Why was the initial entropy so low? This is where physics reaches the edge of its current understanding. There are several proposals, none of them entirely satisfying. One possibility, championed by Roger Penrose, is that there is some as yet undiscovered law of nature, some principle of quantum gravity that constrains the initial conditions of the universe to be low entropy. Penrose has proposed a specific version of this idea called the Weyl curvature hypothesis, which states that the gravitational degrees of freedom were highly constrained at the Big Bang. This is an attractive idea, but we have no proof that such a law exists. And without a theory of quantum gravity, we cannot derive it from first principles. Another possibility, explored by Carroll and his collaborator Jennifer Chen, is that the low entropy beginning of our universe is not special at all, but rather a natural consequence of the dynamics of a much larger multiverse. In their model, our Big Bang is one of many, a fluctuation in an eternally inflating space, and the arrow of time in our universe is just a local phenomenon, pointing away from the moment of lowest entropy in our particular cosmic neighborhood. In a sufficiently large multiverse, regions of low entropy are inevitable, and observers like us can only exist in those regions where entropy is increasing, because that is the only condition under which complex structures, including brains, can form. Cosmic inflation, the theory that the universe underwent a brief but incredibly rapid period of expansion in its first fraction of a second, is part of the standard cosmological model and helps explain many features of the observed universe, including its remarkable uniformity on large scales. But inflation by itself does not solve the past hypothesis. If anything, it makes the puzzle deeper. Starting inflation requires even more special, even lower entropy initial conditions than the standard Big Bang model. Inflation smooths things out beautifully, but it needs something to get it going, and that something has to be very precisely arranged. The honest answer, the answer that physicists will give you if you press them, is that we do not know why the universe started with low entropy. This is an open question. It is one of the most important open questions in all of physics, and it may be that the answer requires a theory of quantum gravity, a theory we do not yet possess. It may be that the answer lies in the nature of the Big Bang itself, in the quantum origin of spacetime, in the deep structure of reality at scales we cannot yet probe. Or it may be that the question, in some form, is unanswerable, a brute fact about the universe that has no deeper explanation, like the particular values of the fundamental constants. Whatever the answer, the implication is the same. The arrow of time, the fact that yesterday is different from tomorrow, that we age and never grow younger, that broken things stay broken. All of it traces back to a single extraordinary fact about the beginning of the universe. The cosmos started in a remarkably special, remarkably improbable, remarkably low entropy state. And it has been moving away from that state ever since. If time's arrow is rooted in the initial conditions of the universe, then to truly understand the arrow, we need to understand the relationship between time and the physical structure of the cosmos. And there is no better guide to that relationship than Albert Einstein. We have already touched on Einstein's revolutionary insight that time is not absolute. But the full implications of his work are so profound, so counterintuitive, so deeply strange, that they deserve a closer look. Because Einstein did not merely show that time is relative. He showed that time is physical, that it is part of the geometry of the universe, and that it is inseparable from space. In Special Relativity, published in 1905, Einstein showed that time passes at different rates for observers moving at different speeds. This is not a trick of perception or a failure of clocks. It is a fundamental feature of the universe. If you and a friend synchronize your watches, and then your friend boards a spaceship and travels at 90% of the speed of light for what feels to her like 1 year, and then returns, she will find that more than 2 years have passed on Earth. She has not merely experienced time differently. She has aged less. Her cells have divided fewer times. Her heart has beaten fewer times. Time itself, in a real, physical, measurable sense, ran more slowly for her. This effect, called time dilation, has been confirmed to extraordinary precision. Atomic clocks carried on aircraft tick at measurably different rates than identical clocks left on the ground. The GPS satellites orbiting the Earth must account for time dilation, both from their speed and from the difference in gravitational strength at their altitude, or their navigation signals would drift by miles per day. Time dilation is not theoretical, it is engineering. In General Relativity, published in 1915, Einstein went further. He showed that gravity is not a force in the Newtonian sense. It is a curvature of spacetime caused by the presence of mass and energy. And that curvature affects time directly. The stronger the gravitational field, the more slowly time passes. Clocks on the surface of the Earth tick slightly more slowly than clocks on a mountaintop. Clocks near a neutron star tick much more slowly than clocks far away. And clocks near the event horizon of a black hole slow to a crawl, until, at the horizon itself, from the perspective of a distant observer, they stop entirely. This is not merely an analogy or an approximation. Time, near a black hole, really does nearly stop. If you could watch someone falling into a black hole from a safe distance, you would see them slow down, their movements becoming sluggish, their light shifting toward the red end of the spectrum, until they froze at the edge of the event horizon, forever suspended in a single instant. From the falling person's own perspective, of course, nothing unusual happens. They pass through the horizon in finite time and continue falling toward the singularity at the center. But the two perspectives are both valid, both real. Time is not universal. It is local, personal, tied to the geometry of the spacetime through which you are moving. And at the singularity, at the point of infinite density at the heart of a black hole, the equations of general relativity break down entirely. The curvature of spacetime becomes infinite. The concepts of space and time, as we understand them, cease to have meaning. It is widely believed that this breakdown signals the need for a theory of quantum gravity, a theory that can describe what happens when spacetime itself is pushed to its limits. Black holes are also intimately connected to entropy and the arrow of time. In the early 1970s, the Israeli physicist Jacob Bekenstein proposed that black holes have entropy, and that their entropy is proportional to the area of their event horizon. Hawking initially resisted this idea, but his own calculations, showing that black holes emit a faint glow of thermal radiation, now called Hawking radiation, confirmed it. The entropy of a black hole is enormous. A black hole with the mass of the Sun has an entropy of roughly 10 to the 77, vastly larger than the entropy of the Sun itself. This means that when matter collapses to form a black hole, the entropy of the universe increases enormously. Black holes are, in a sense, the ultimate entropy dumps, the maximum entropy objects in the cosmos. They represent the final state toward which gravitational entropy is always driving. This connection between black holes and entropy deepens the mystery of the arrow of time, because it reinforces the point that the smooth, black hole-free early universe was a state of extraordinarily low gravitational entropy. The universe has been creating entropy ever since, through the formation of stars, galaxies, and eventually black holes. And the arrow of time has been pointing along that slope of increasing entropy all along. Let us push even deeper into the relationship between time and gravity, because it leads to one of the most beautiful and haunting ideas in all of physics. Imagine you are standing on the surface of a neutron star, a collapsed stellar remnant so dense that a teaspoon of its material would weigh about 6 billion kilograms on Earth. The gravity on the surface of a neutron star is about 200 billion times stronger than the gravity on Earth. And because of general relativity, time on the surface of that neutron star ticks measurably slower than time far away. If you spent 1 year on the surface and then returned to Earth, you would find that more than 1 year had passed here. Depending on the specific neutron star, the difference could be significant, perhaps 5 or 10%. Now imagine something even more extreme. You are falling toward a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. As you approach the event horizon, the boundary of the black hole, time dilation becomes more and more extreme. To a distant observer watching you fall, your clock appears to slow down. Your movements become sluggish. The light from your body shifts to longer and longer wavelengths, reddening, dimming, until you appear to freeze at the edge of the event horizon, an eternal image imprinted on the boundary of the black hole. But from your own perspective, you notice nothing unusual as you cross the horizon. Your clock ticks normally. Your heart beats at its usual rate. You pass through the horizon and continue falling into the interior of the black hole toward the singularity at its center, where the curvature of space-time becomes infinite and the known laws of physics break down. This dramatic difference in the experience of time between different observers is not a failure of our understanding. It is a feature of reality. Time is genuinely, physically different for different observers. There is no absolute clock. There is no universal now. Each observer carries their own personal experience of duration, shaped by the geometry of the space-time through which they are moving. And inside the black hole, something even stranger happens. The roles of space and time reverse. In ordinary space-time, you are free to move in any direction in space, but are compelled to move forward in time. Inside a black hole, the mathematics of general relativity shows that the radial direction toward the singularity takes on the character of a time-like direction. You cannot avoid moving toward the singularity any more than you can avoid moving forward in time. The singularity is not a place in space. It is a moment in time. It is your future. It is everyone's future who crosses the event horizon. And it is unavoidable. This is perhaps the most dramatic illustration of the connection between time and gravity. Inside a black hole, the geometry of space-time itself forces you to move in a specific direction, toward a specific end. The arrow of time inside a black hole is not just a statistical tendency. It is a geometric inevitability. We have seen that the arrow of time is connected to entropy. That entropy is connected to the initial conditions of the universe, and that the initial conditions of the universe are connected to the birth of space-time itself. But there is yet another layer to the mystery, a layer that strikes at the very foundation of physics, and it is called the problem of time. The problem of time is a difficulty that arises when you try to combine quantum mechanics with general relativity. In ordinary quantum mechanics, time plays a special role. It is the background parameter that tells you how a quantum state evolves. The Schrödinger equation, the central equation of quantum mechanics, describes how the wave function of a system changes with time. Time in quantum mechanics is not something that is measured by the system. It is the external clock against which all measurements are made. But in general relativity, there is no external clock. Time is part of the system. It is part of the dynamical, evolving, curving space-time. There is no outside observer with a clock. Time is not a background. It is one of the things being described. When physicists tried to combine these two frameworks in the 1960s, they ran into a bizarre and troubling result. In 1967, the American physicist Bryce DeWitt, building on earlier work by John Archibald Wheeler, wrote down what he hoped would be the fundamental equation of quantum gravity. It is now called the Wheeler-DeWitt equation, and it has a remarkable property. There is no time in it. The Wheeler-DeWitt equation describes the quantum state of the entire universe, but it is an equation in which nothing changes. The wave function of the universe, according to this equation, is static, frozen, timeless. There is no evolution. There is no past or future. The universe simply is. This is sometimes called the frozen formalism problem, and it has been a source of intense debate and confusion for more than half a century. If the fundamental equation describing the quantum universe contains no time, then where does the time we experience come from? How does the flowing, changing, era of time-laden world we live in emerge from a timeless quantum description? There are many proposals. One approach, called the semi-classical approximation, suggests that time emerges in the limit where quantum effects become small and the universe behaves approximately classically. In this picture, the timeless wave function of the universe contains within it many possible classical histories, each one a universe evolving in time. And our experience of time arises because we inhabit one of these histories. Time is not fundamental. It is emergent, an approximate, large-scale description that breaks down at the Planck scale. Another approach, called the Page-Wouters mechanism, named after the physicists Don Page and William Wouters, suggests that time arises from quantum entanglement between different parts of the universe. Even though the total state of the universe is static, the correlations between subsystems can give rise to an effective time evolution. If you use one subsystem as a clock and measure the state of the rest of the universe relative to that clock, you find that the rest of the universe appears to change in time. Time, in this picture, is a relationship between parts of the universe, not a fundamental property of the whole. These ideas are speculative and far from settled. The problem of time remains one of the deepest unsolved problems in theoretical physics, but what is remarkable is the possibility that lurks behind them. The possibility that time, the most intimate and familiar feature of our existence, is not fundamental at all. That at the deepest level of reality, at the Planck scale, where quantum gravity reigns, there is no time. That the flow of moments, the arrow from past to future, the ticking of clocks and the beating of hearts, is all an emergent phenomenon, arising from something deeper and stranger, something we do not yet have the language or the mathematics to describe. The idea that time might be emergent, that it might not be fundamental to the deepest layer of reality, is one of the most radical ideas in modern physics. But it is not as new as it might seem. Its roots go back more than a century, to the debates between Boltzmann and his critics, and even further, to the ancient philosophers who wondered whether time was a feature of the world or a feature of the mind. The Stoic philosophers of ancient Greece believed that time was inseparable from change. Without change, they argued, there is no time. If nothing moves, nothing decays, nothing transforms, then in what sense can we say that time passes? This view has echoes in the work of the modern physicist Carlo Rovelli, who has argued that the fundamental equations of physics describe relations between physical quantities. not the evolution of those quantities in time. Time, in Ravelli's view, is not a container in which events happen. It is a label we attach to certain patterns of change. The philosopher Immanuel Kant, writing in the 18th century, took a different approach. He argued that time is not a feature of the external world at all, but a feature of the human mind, a lens through which we organize our experience. Time, for Kant, is a form of intuition, a precondition for perception, something that we bring to the world rather than something we find in it. Modern physics offers no definitive resolution to these ancient debates, but it adds new dimensions to them. The Wheeler-DeWitt equation, with its frozen, timeless wave function of the universe, suggests that at the deepest level, the universe may indeed be static. The block universe of general relativity, in which past, present, and future coexist, suggests that the flow of time may be an illusion. And yet, the second law of thermodynamics, with its relentless increase of entropy, seems to ground the arrow of time in something objective, something physical, something real. Perhaps the deepest insight is that these perspectives are not as incompatible as they seem. Perhaps time is emergent in the same way that temperature is emergent. Temperature is not a fundamental property of individual atoms. An individual atom does not have a temperature. Temperature is a statistical property of large collections of atoms, a description that only makes sense at the macroscopic level. And yet, the temperature is real. It has physical consequences. It determines whether water freezes or boils, whether stars shine or collapse, whether life can exist. Temperature is emergent, but it is not illusory. Time may be similar. At the Planck scale, in the quantum foam of the very early universe, there may be no time. But at the macroscopic scale, in the world of stars and planets and people, time emerges from the underlying quantum geometry, in the same way that temperature emerges from the motions of atoms. And the arrow of time, the direction from past to future, emerges from the initial conditions of the universe. In the same way that the flow of heat from hot to cold emerges from the statistical properties of large numbers of particles. If this is correct, then the birth of time is not a single, dramatic event. It is a gradual emergence, a crystallization of order from the quantum chaos of the Planck epoch. Time does not begin with a bang. It seeps into existence, gathering strength and clarity as the universe expands and cools, until it becomes the steady, flowing, arrow-shaped current that carries us from birth to death, from memory to anticipation, from the first light of the Big Bang to the last glow of the dying stars. Before we arrive at the ultimate fate of the universe, let us pause and consider one of the most remarkable insights to emerge from the study of entropy and time, an insight about the nature of life itself. Living organisms are sometimes described as local decreases in entropy, islands of order in a sea of disorder. And this is true in a limited sense. The molecules in your body are fantastically more organized than the same atoms would be if they were scattered randomly through the environment. But this local decrease in entropy comes at a cost. To maintain your internal order, you consume low-entropy food, break it down, and release high-entropy waste heat into the environment. The total entropy of you plus your environment increases, even as your local entropy stays roughly constant. You are not fighting the second law. You are obeying it brilliantly. The physicist Erwin Schrödinger, in his influential 1944 book, What is Life?, was one of the first to articulate this idea clearly. He wrote that living organisms feed on negative entropy, meaning they consume ordered energy and excrete disordered energy. This formulation was imprecise, and it drew some criticism from physicists at the time, but the core insight was correct. Life is a process that exploits the entropy gradient of the universe. It exists because the universe is not in equilibrium. It thrives in the gap between the low entropy past and the high entropy future. And this means that life, in the deepest sense, is a child of the arrow of time. Without the arrow of time, without the increase of entropy, without the flow from order to disorder, there could be no metabolism, no reproduction, no evolution, no thought. The arrow of time is not something that happens to living things. It is the condition that makes living things possible. Consider the sun, which sends a stream of low-entropy visible light toward the Earth. The photons of visible light are relatively few but energetic. The Earth absorbs this energy, uses it to drive the chemistry of life, and then re-radiates the same total amount of energy back into space, but in the form of many more photons of infrared light, each one carrying less energy. The total energy is conserved, but the entropy has increased. The Earth acts as an entropy processing machine, converting the ordered energy of sunlight into the disordered energy of heat. And life is the extraordinary, improbable, beautiful machinery that runs on this conversion. This is why the night sky matters, not just aesthetically, but physically. The fact that the night sky is dark, the fact that the universe is full of cold, empty space, is essential for life. Without that cold sink, there would be nowhere for the waste heat to go. Without the temperature difference between the hot sun and the cold void, there would be no energy gradient to exploit, no work that could be done, no life that could exist. The darkness of the night sky is the canvas on which the arrow of time paints the picture of life. Let us now look the other direction, not backward toward the birth of time, but forward, far, far forward, into the future of the universe and the future of time itself. If the arrow of time points in the direction of increasing entropy, then the arrow has a destination. Entropy is increasing. The universe is expanding. Energy is spreading out, becoming more evenly distributed, less available to do useful work. And this process has an end, a final state, a destination that physicists have been contemplating with a mixture of scientific fascination and existential dread for more than 150 years. It is called the heat death. The concept was first articulated in the 1850s, when Hermann von Helmholtz and William Thomson, Lord Kelvin, realized that the second law of thermodynamics, applied to the universe as a whole, predicted a grim future. If entropy always increases, then the universe must eventually reach a state of maximum entropy, a state of perfect thermal equilibrium where all temperatures are equal. All energy gradients have been smoothed out, and no more work can be done. It would be a universe of total uniformity, a universe of absolute stillness, a universe in which nothing ever changes. Modern cosmology has filled in the details of this long, slow decline, and the picture is both more precise and more haunting than Helmholtz could have imagined. We currently live in what astronomers call the stelliferous era, the age of stars. Hydrogen fuses into helium in stellar cores, releasing energy that powers starlight, and through a chain of processes, supports the existence of planets, ecosystems, and life. But hydrogen is a finite resource. Stars are burning through it. In roughly 100 trillion years, all the hydrogen will be exhausted, and the last stars will flicker and die. The age of stars will end. After the last star dies, the universe will enter an era of darkness. The only objects remaining will be stellar remnants, white dwarfs cooling slowly toward absolute zero, neutron stars spinning down into silence, and black holes, the gravitational tombs of the most massive stars. These objects will drift through an expanding, emptying void, growing colder and dimmer with each passing eon. But even the black holes are not eternal. In 1974, Stephen Hawking made one of his most celebrated discoveries. He showed that black holes are not truly black. They emit a faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries away energy, and over immense stretches of time, the black hole shrinks. The most massive supermassive black holes, the ones at the centers of galaxies, are expected to take roughly 10 to the 100th years to evaporate. That number is so large that writing it out in full would require a 1 followed by 100 zeros, a number incomprehensibly larger than the current age of the universe. But eventually, even the black holes will be gone. They will evaporate in a final burst of radiation, leaving behind only a thin, cold soup of particles, photons, neutrinos, and perhaps some exotic remnants, drifting through an ever-expanding space at temperatures asymptotically approaching absolute zero. At this point, the universe will have reached something very close to maximum entropy. There will be no temperature differences to drive heat engines, no energy gradients to power chemical reactions, no structures of any kind. The distinction between past and future will blur because there will be nothing left to change. The arrow of time, which arose from the low entropy conditions at the Big Bang, will have run its course. It will have nowhere left to point. But is this truly the end? Some physicists have suggested that it might not be. The theoretical physicist Julian Barbour, in his book The Janus Point, argues that the heat-death hypothesis may be based on a misunderstanding of the second law. Barbour points out that the second law has been tested on systems with well-defined boundaries, like gases in containers. But the universe as a whole has no container. It is expanding, and as it expands, the maximum possible entropy increases faster than the actual entropy. This creates what the cosmologist David Laser called an entropy gap, a growing difference between the actual entropy of the universe and the maximum possible entropy. As long as this gap exists, there is room for structure, complexity, and perhaps life. Roger Penrose has proposed an even more radical idea, his conformal cyclic cosmology, which suggests that the heat-death of one cosmic era, which he calls an eon, becomes the Big Bang of the next, when the universe has expanded to the point where only massless particles remain. The distinction between large and small distances becomes meaningless, and the geometry of the dying universe becomes indistinguishable from the geometry of a new Big Bang. The cycle repeats forever. Time's arrow is not extinguished at the heat death, it is reborn. These ideas are speculative, and they remain at the frontier of theoretical physics. But they hint at something profound. The fate of time is tied to the fate of the universe, and we do not yet know what that fate will be. And so, we arrive at the deepest question of all. What is time? Is time a fundamental feature of reality, woven into the fabric of the universe at the most basic level? Or is it an emergent phenomenon, arising from something deeper, something we have not yet glimpsed? There are physicists on both sides. Some, like the philosopher Tim Maudlin, argue that the passage of time is a basic, irreducible feature of the world, that the production of the future from the present is as fundamental as anything in physics. Others, like Julian Barber, argue that time is an illusion, that at the deepest level, the universe is timeless, and our experience of a flowing present is a trick played on us by the configuration of the cosmos. Einstein himself leaned toward the latter view. His general theory of relativity treats time as a dimension, much like the three dimensions of space. The past, present, and future all exist, laid out like a landscape, a four-dimensional structure that physicists call the block universe. In the block universe, there is no objective now. There is no moment that is singled out as the present. All moments are equally real. The flow of time is an artifact of our perspective, a consequence of the fact that we are embedded in the block, experiencing it one slice at a time. But the block universe has its critics. It seems to conflict with our deepest intuitions about the nature of experience. If all moments are equally real, then in what sense is the future open and undetermined? In what sense do we have free will? In what sense is the present special? Lee Cronin, a chemist at the University of Glasgow, has argued forcefully that time is not emergent, but fundamental. He points out that physicists have concluded time is emergent, and the universe somehow exists in a timeless state. But we have no evidence that time travel backward is possible. We have only ever experienced time moving in one direction. The passage of time, Cronin argues, is the resource that allows things to happen. Without it, nothing can occur. He suggests that it is space, not time, that is emergent, and that the Big Bang is merely the point in time at which space emerged from a deeper, temporal reality. Carlo Rovelli, one of the founders of loop quantum gravity, takes yet another approach. In his book, The Order of Time, Rovelli argues that time, at the fundamental level, does not exist. The Wheeler-DeWitt equation describes a timeless universe, but Rovelli suggests that what we call time is actually a manifestation of our ignorance. Because we cannot track every microscopic detail of the universe, we perceive a simplified, coarse-grained picture. And in that picture, there is an apparent flow of time. Time, for Rovelli, is a product of thermodynamics, of entropy, of the blurring of details. It is real in the same way that temperature is real. Temperature is not a fundamental property of individual atoms. It is a statistical property of large collections of atoms. Time, perhaps, is similar. A statistical, emergent, approximate description that breaks down when you look closely enough. These debates are far from resolved. They may never be fully resolved, at least not until we have a complete theory of quantum gravity. A theory that can describe the universe at the Planck scale, where the distinction between space and time dissolves into quantum uncertainty. Such a theory is the great white whale of theoretical physics, hunted for nearly a century, but never captured. But whatever the answer turns out to be, certain things seem clear. Time, as we experience it, is deeply connected to entropy. The arrow of time, the felt direction from past to future, is a consequence of the universe's remarkably low entropy beginning. And the birth of time, if it can even be called a birth, is entangled with the birth of the universe itself, with the emergence of space-time from some quantum gravitational origin that we do not yet understand. We are creatures of time. Our entire existence, from the first breath to the last heartbeat, unfolds within its flow. We mark its passage with rituals and calendars, clocks and calendars. We mourn its loss. We treasure its gifts, and yet, despite all our science, despite the equations of Einstein and Boltzmann, and Clausius and Hawking and Carroll, despite the extraordinary precision with which we can measure its passage, we still do not fully understand what it is. Perhaps that is fitting. Time has always been a mystery, from the ancient philosophers who debated whether it was real or illusory, to the modern physicists who see it dissolving in their equations. But the mystery is not a failure of understanding. It is an invitation to look deeper, to think harder, to push the boundaries of knowledge further into the unknown. 13.8 billion years ago, something happened. Space-time came into existence. The universe was born in a state of extraordinarily low entropy, a state so improbable, so finely arranged, that it set in motion the entire story of cosmic history. Stars formed, galaxies assembled. On at least one small, rocky planet orbiting an ordinary star in an ordinary galaxy, molecules arranged themselves into patterns complex enough to look up at the night sky and wonder about the nature of the stars, about the structure of the atom, about the curvature of space-time, and about the deepest, most intimate, most universal feature of their existence: the flow of time, the arrow that carries us from the first cry of birth to the silence of the grave. The arrow that turns eggs into omelets and never the reverse. The arrow that makes memory possible, that makes cause and effect possible, that makes life itself possible. That arrow was born with the universe. It was set in motion by the extraordinary conditions at the beginning of everything. It is sustained by the relentless increase of entropy, the unstoppable march from order toward disorder, and it will continue to point forward from past to future, for as long as there is entropy left to increase. For as long as there is a difference between what was and what will be, and when the last star has burned out, when the last black hole has evaporated, when the universe has finally reached its state of maximum entropy, and there is nothing left to change, the arrow may, at last, come to rest, not because time has ended, but because, with nothing left to distinguish past from future, the question of which direction time flows will have lost all meaning. Until then, the arrow flies, and we fly with it. There is something deeply moving about the fact that we can even ask these questions. The universe produced creatures capable of contemplating their own origins, capable of tracing the arrow of time back to its source, capable of wondering whether time itself is fundamental or an illusion. This is not a trivial accomplishment. The atoms in your brain are the same kinds of atoms that exist in rocks and rivers and the empty void between galaxies. They obey the same laws. They are subject to the same forces, and yet arranged in just the right way, shaped by billions of years of evolution on a planet bathed in the low entropy light of a star. They can think about themselves. The philosopher Thomas Nagel once asked, "What is it like to be a bat?" We might ask a deeper question. What is it like to be a collection of atoms that knows it is a collection of atoms? What is it like to be a temporary eddy in the great river of entropy? A brief, local decrease in disorder, aware of the current that carries it. We do not know. We may never fully know, but the asking of the question is itself a kind of answer. It tells us that the universe is not merely a machine grinding toward equilibrium. It is a machine that, along the way, produces pockets of extraordinary complexity, including pockets complex enough to contemplate the machine itself. This is what the arrow of time has given us. Not just aging and decay, not just broken glass and cold coffee, but also growth and creation. Stars and galaxies, mountains and oceans, music and mathematics, love and loss, and the bittersweet awareness that all of it is temporary. All of it carried along by the same irreversible current that turns eggs into omelets, and never the reverse. The physicist Brian Cox once said that the arrow of time is the reason anything interesting happens at all. Without it, the universe would be a featureless, changeless equilibrium, a cosmic fog of uniformity in which nothing could exist, nothing could happen, and nobody could wonder why. The arrow of time is not a curse. It is a gift. It is the engine of change, the condition of possibility, the reason there is something rather than nothing. And so, as we sit here together at this particular moment in the long history of the cosmos, roughly 13.8 billion years after the beginning and trillions of years before the end, we occupy a remarkable window, a window in which the entropy of the universe is high enough for complex structures to exist, but low enough, relative to its eventual maximum, for those structures to still do interesting things. We live in the sweet spot, the age of stars, the age of chemistry, the age of life, the age of thought. It will not last forever. Nothing does. The arrow guarantees it. But for now, right now, in this fleeting, improbable, beautiful moment, the arrow flies, and we are here to watch it. You have been watching the entire history of the universe. If this journey through time meant something to you, if it made you think or wonder or see the universe a little differently, then please take a moment to hit the like button and subscribe to the channel. Leave a comment and tell us what you think. Do you believe time is fundamental? Or do you think it is an illusion? We would love to hear your thoughts. Thanks for watching, and we will see you next time.